This video is about more guidelines for powers of secant and tangent. In the last video we talked about these two guidelines. The first was if the power of a secant is even and positive, then we save a secant squared for du. And let u equal tangent of whatever your angle is, usually kx. And then of course you're going to have to use the fact that 1 plus tangent squared of some angle equals secant squared of the same angle to get all of your secant factors, your secant squared factors written in terms of tangent. And that is, we're talking about the secant squared factors that have not been saved for du, so the ones that we've been leaving in brackets in the other videos. We also said that if the power of tangent is odd and positive, we want to let u equal secant this time, and we're going to save a secant factor and a tangent factor for du and let u equal secant of kx. And then of course you're going to write everything else, everything other than that secant and that tangent, entirely in terms of secant, using this identity again. Yeah, you might have to rearrange this. You're going to have to replace every tangent squared with a secant squared minus 1 in order to use this guideline. But again, the idea is we're going to save part of it for du, and then we're going to write everything else in terms of u, and then we're just going to use the power rule to anti-differentiate in both cases. Now, it gets a little tricky if neither one of these work. If the power of secant isn't even, but it's odd, and the power of tangent isn't odd, but it's even, then we're going to have to do something else. Some possibilities are, you might try these. So you might try writing secant of kx as 1 over cosine, and tangent of kx can be written as sine over cosine. And simplifying from there, so that your integral or your integrand now involves powers of sine and cosine. And then you just go to your sine and cosine rules, and of course you want to remember your reciprocal identities and your two Pythagorean identities that we've talked about. So that's another possibility. A fourth possibility is if the power of secant is odd, we can try integration by parts. I know it seems a little strange, but it works. You might let or save a secant squared factor for dv, and then use integration by parts. Now this is a special problem in that you end up with the integral of your secant to that odd power on the left-hand side and the right-hand side of an equality, and you have to solve for the integral. And I'll show you an example of that in a minute. If the power of tangent is even, I guess this is odd and positive, and this one should be even and positive. You might replace any tangent squared factor, tangent squared of some angle, with secant squared minus 1 of that angle, or secant squared of that angle minus 1, excuse me. That might work. These last three are a little iffy. This sometimes works, this sometimes works. In the worst case scenario, this number 3 works. You can write everything in terms of sine and cosine and see what happens from there. Yeah, it's not as clear as it was with the powers of sine and cosine. So let me show you a couple more examples. Let's say we're looking at secant cubed of, let's say, pi x. Well, since the power of secant is odd and positive, we're guided to try saving a secant squared for dv and using integration by parts. So I've got secant cubed is the same as secant times secant squared. So we're going to do that. And then we're going to do integration by parts. So this is our u, and we're going to let dv be secant squared. And the reason we let dv be secant squared is because the antiderivative of secant squared is tangent. Keep the angle the same, don't forget to divide by k. And then the derivative of secant is something that we can do. Derivative of secant is secant of the angle times tangent of the angle times the derivative of the inside by the chain rule. Don't forget to multiply by dx. So we get, according to integration by parts, u times v minus the integral of v du. So we have 1 over pi times secant times tangent minus the integral of v times du. That 1 over pi times pi is just a 1. And then I've got a secant. And tangent times tangent is tangent squared. Now watch this. This is equal to this. By integration by parts, these two guys are equal to each other. But if I want to, I can replace this tangent squared with secant squared minus 1 again. And watch what happens when we distribute. I'm thinking of this as a separate line of thought. I've got this up here is equal to this down here. Secant times secant squared is secant cubed. And I've got a negative secant times a negative 1 is a positive secant. Writing that as a separate integral. Oops. There, my computer's in the way. I have a rule for that. Now notice you've got a secant cubed of pi x on this side and a secant cubed of pi x on this side. Sometimes I would worry about that. Sometimes I would say, uh-oh, am I doing something that's circular? are all of these going to cancel out, and eventually I'm just going to be left with integral of secant cubed equals integral of secant cubed. Now, that could happen, and I would be worried if that was a plus secant cubed and not a minus secant cubed. But notice it's a minus secant cubed. So what I really have is an equation right now. I've got this secant cubed equals all of this, and the thing that I'm looking for is this integral. It appears on both sides. Let me bring this down here. So this is basically what I'm saying. Secant cubed, the integral of secant cubed of pi x is equal to this function minus the thing I'm looking for, plus this, which is known. I can just write it down as my antiderivative. But the thing I'm looking for is on both sides. Just as an aside, this is like solving this. What if you had x equals 2 minus x plus 3? That's all it is. My unknown equals something minus the thing I'm looking for plus something else. How do you get x by itself? Well, if you said just add the x to the other side and then divide, you'd be right. If we add that x to the other side, we get 2x and then divide by 2, and you find out that x is 5 divided by 2. Yeah, nice and easy. This is exactly the same thing. It looks much worse, but it's exactly the same thing. The thing I'm looking for is on the left-hand side and the right-hand side. So if I add this to both sides, let's use that little aside. I'm going to add that integral to both sides. Just adding vertically. Probably been a while since you did that. That guy reduces, and now I just have 2 of the thing I'm looking for on the left-hand side. And on the right-hand side, I've got 1 over pi, secant of pi x times tangent of pi x. And the integral of secant of pi x is natural log of the absolute value of secant plus tangent. Don't forget your plus c. Now remember, with antiderivatives, the angle stays the same. So that angle was pi x. I'm going to have a pi x inside. Since there is a k multiplying my x, if I took the derivative, I'd have to multiply by the k or multiply by the pi. Since I'm taking the antiderivative, I need to divide by the pi. All right, and I was looking for the integral of secant cubed. Got 2 of them. So 2 of those integrals is this. Are this? I don't know. I teach math, not grammar, right? So I've got this equals this, and if I'm trying to get this integral of secant cubed by itself, I have to divide by 2. Or alternatively, you could divide each term by 2, or you could say dividing by 2 is multiplying by 1/2. So I get this equals, next page, the integral of secant cubed of pi x equals 1 over 2 pi times secant of pi x, tangent of pi x, plus 1 over 2 pi times natural log of the absolute value of secant of pi x plus tangent of pi x plus c. All right, that's my answer. Okay, so that's our example, and let's look at our guidelines again. We just did one like this, example of guideline number 4. So this is example 1 on this video. Now I'd like to look at the case when the power of tangent is even and positive. Let's do a couple like this. Okay, you can see why it works. Do the easiest one first. You always practice with a k in front of the x. It's good to to remind you of how that works. Now I don't have a rule for tangent squared in my table, but remember we have a rule for secant squared. And tangent squared is secant squared minus 1 because of our Pythagorean identity. So this is equal to secant squared minus 1. Angle stays the same. And now we take the antiderivative. Antiderivative of secant squared is tangent of the same angle. We've got a k out front, don't forget to divide by the k. And the antiderivative of 1 with respect to x is just x plus z. So that's how it works if it's just tangent squared. I guess the question is, well, what if it's, looking at even powers of tangent, what if it's tangent to the 4th? And to simplify things, I think I'm just going to make that an x this time. Let's make it nice and simple. Well, our guideline tells us factor out one of those tangents. So you've got tangent squared x times tangent squared x dx. And then replace this tangent squared with secant squared minus 1, just like you did up there. And distribute. So you've got tangent squared times secant squared. And then tangent squared times a negative 1 is negative tangent squared. Okay, so just to recap before we go any further, the guideline said if the power of tangent is even and non-negative, factor out a tangent squared, then you want to replace tangent squared with secant squared minus 1. And then once you've done that, distribute. Now this one we can solve with a U-substitution. Because I've got a secant squared x dx, I could let u equal tangent. So anything that involves this secant squared factor can now be handled with a u-sub. So for this part, we want to let u equal tan x, and then du will be secant squared x dx. So that's what this guideline has gotten us. It got us from here down to here. And you say, well, what about that tangent squared? Well, you can just do what we just did again. So I said, do all of this, and then as necessary, you might have to repeat. I don't have a rule for tangent squared, but I've got a rule for secant squared minus 1. So I can replace that tangent squared with secant squared minus 1 and then just anti-differentiate that. So let's finish this one. I've got tangent squared x times secant squared x dx, and then I'm subtracting. Let's do the integral of secant squared x minus 1. This one is the u-sub. If u is tangent, that's u squared. If u is tangent, du is secant squared, so that's just the integral of u squared du. Power rule, nice and simple. Add 1 to the exponent, divide by the new exponent. Replace u with whatever it was in terms of x. In this case, it was tan x. And then over here, that's easy. The antiderivative of secant squared is tangent. And the antiderivative of negative 1 with respect to x is negative x. Negative x times negative 1 is positive x. So that's how we handle even powers of tangent. Now what if we did tangent squared, we have tangent to the fourth, I want to do one more. Let's do tangent to the sixth. And again, I'm just going to make my angle x instead of kx to simplify things for us. I just want you to see how this process works. Guideline said, take your tangent to the sixth, because the power of tangent is even and non-negative, or even and positive, and factor out a tangent squared, and replace that tangent squared with secant squared minus 1. And distribute. So I've got tangent to the fourth times secant squared minus tangent to the fourth times negative 1. For this guy, I can do the u sub, very similar to what we did up here. It's going to be u to the fourth du. For this guy, tangent to the fourth, well, isn't that just the last problem that we did? We're just going to do it again. So I replace tangent to the fourth with tangent squared times tangent squared. And tangent squared is secant squared minus 1. We distribute. Negative tangent squared times negative 1 is positive tangent squared. And we don't have a rule for that, but we can replace that with secant squared minus 1 as well. So you just really keep going. You just keep doing this. And these two guys, since they both have a secant squared in common, I'm going to do the u sub for both of them. I'm going to factor out the secant squared, factoring it off to the right instead of the left, because I'm saving it for du. And that last tangent squared I'm replacing with secant squared minus 1. Because I don't have a rule for that, but I've got a rule for that, and I've got a rule for that. So this is the u sub, and those are basic rules. With u equals tan x, du is secant squared x dx. So that's just du. That's u to the fourth minus u squared. So we're here. The antiderivative of secant is, or secant squared is tangent of x. The antiderivative of negative 1 is negative x with respect to x. Just do the power rule here. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. This guy already took care of our plus c. Last thing to do is back substitute. I'm just leaving space for my trig functions. Do those in a different color. U was tan x, so that's tan x to the fifth. And this is tan x to the third. And don't forget your other two pieces. So you see how that works. If the power of tangent is odd, or excuse me, even, we can follow this pattern. This was the fifth of our guidelines. I think it might be different on your formula sheet. It might be third or fourth, but that's the one that we just did. That was examples 2, 3, and 4. We did tangent squared, tangent to the fourth, and tangent to the sixth. And for example 1, we did the integral of secant cubed. The integral of secant to the fifth is similar. It's just longer. So I'm not going to do that in this video. Now, if none of these are true, well, actually, either this one's going to be true, power of secant is even and positive, you can do this, or the power of secant will be odd and positive, so you can do this. 4 and 5 work particularly well when we've got a secant that's odd and positive and there are no tangents, and we have number 5 works particularly well when we have a power of tangent that's even and positive and there are no secants. But there are cases, sort of mixed cases, when this would work, but maybe it's not obvious. So if I've got a secant times tangent squared, replacing the secant times tangent squared with secant times secant squared minus 1 would lead us to this place where we have the secant cubed. And then once we have the secant cubed, we would have to use number 4. So with a problem like this, it's kind of mixed and a little bit hard to see. But you just try whatever you have. You try something on the list. So actually, it looks like if I was working with secant times tangent, it's kind of a hybrid. It's this one and this one at the same time. So we'd have to do both. We replace the tangent squared by secant squared minus 1, and then we say, okay, now what do I do from here? Now I've got an odd power of secant, so I'm going to have to follow number 4. Much, much less straightforward than the powers of sine and cosine that we looked at in our first video over trigonometric integrals. Now sometimes you get really lucky, and if none of the rules apply, sometimes writing everything in terms of sine and cosine will work really nicely. And I think I'm going to show you how to do that in the next video.